Hello everyone. Today I'm going to show you the new feature I put in the etracer software. The ability to plot a graph with the grid voltage as the x-axis. Okay. This feature is requested by an etracer user from UK. His name is L. Moglia. He has a website, the Batola Valves. And okay, so the new software version is 2.14 alpha, and I'll use a couple of measurement files as example. So first of all, I'll use a measurement data of a 6C4. 6C4 is half of approximately half of the 12AU7 tube. Okay, so here is the measurement data, and you can see the graph is all the dots. Each dot is a measurement data from the from etracer. Okay. So the new feature is at the very beginning, I thought it's easy to implement, but later I found it's quite tricky. One major reason of it is the major data here. Let's say, for example, for scan, the setup file is the high voltage swings from 0 to 500 volts at with a step of 25 volts. So in other words, each step we set up the target voltage at multiple of 25. For example, this one is 25, 50, 75, and 100 volt, and so on and so forth. Okay, but the real measured voltage can differ from this value because the design of etracer uses a capacitor to set up the target voltage. And when the capacitor discharge during the measurement time, the measured voltage will drop compared to this configured value. For tubes like the 12XM or 12AU7, these tubes that draws a small amount of current, this problem is not significant. But if we are testing but for testing power tubes, for example 300B or 6L6, and the voltage drift cannot be ignored. So in order to plot the curves using grid control voltage as the x-axis, we need a very accurate plate voltage for each curve. So I have to use interpolation for that purpose. So okay, let me uncheck the markers. So once we use that mode, we actually realize our interpolation. So this button turn on the miscellaneous plus features. Open this window, and in this window we can draw the graphs in a different way. So starting from this window, every curve you see here is a result of interpolation. So these curves are no longer the major data from the device under test. They are actually from the result of interpolation. So each curve is a model, is a function in the program. Okay, so here we can configure the source for x-axis, source for y-axis, and there's a mass function we can apply on the y-axis, and the range we can set the range, or we can use auto range to automatically set out the range. For the interpolation, I have so we have to select between the mu-based interpolation or GM based, like the I don't remember, basic prompts tool. So we have to the program will automatically automatically set up this option for you. But if you think the detection is wrong, you can configure it. And for some tubes, actually for a lot of tubes, both mode works. So for example, for this tube is the if a tube the internal resistance, internal impedance is not too high or too low. Too high means like tens of k-ohms. Too low means can be I don't know 1k or 1 kilo ohms or 2 kilo ohms or so, and both method works. But there's a tiny difference as you can see when I click on different approaches. There's a slightly change on the interpolated data. So for a triad, we can force it to use the mu-based algorithm. So if it's not selected correctly, you can force it by clicking on this button. And here we have an option to do interpolation. As I said, all the curves are functions, models. And so based on the models, we can actually interpolate these lines and create more lines. So we can have, for example, the interpolation time is set to 2. So each curve is, there's one more curves between the measured data. So if you look at the legend here, the original step on the grid is -2 volts. So from the blue curve to purple lobe, 2 times blue to green. Blue to green is -2. So blue to green is -2, and here we have a -1, -2, -3, -4, -5. We have with this interpolation, we actually derive a curve set that with a voltage step of -1 volt on the grid. We can even interpolate more. For example, we can do X4, then gives us more data point. Okay, and this graph section, we can, as usual, we can set the title, and we can turn on or turn the legend on and off. And this button is when we configure, for example, a different value for this data maximum of data and minimum for the axis. We can redraw it by click on this button. Okay, and so that's pretty much of it. So let's click on the auto range first, and like I said, the major feature for this function is to provide a mode that uses the grid voltage as the axis. So once we click on it, we can see the grid voltage is on the x-axis. If we turn on the legend, we can see the plate voltage is represented by each curve. Okay, so we can play with the interpolation times. That will gives us, because of interpolation, we can have sometimes we can have more data points in the higher current region. Okay, here we can select the different interpolation method. So let's go back to the this only works for when the grid voltage is used as x-axis. So for example, if we use, there are 4 options. This the default option is monotonic piecewise cubic interpolation. What this means is the interpolated curve is guaranteed to be differentiable at each point, but there can be a broad change for the first order of the derivative. Okay, that's it. The linear is piecewise linear, so you can see this the data points is connected by straight lines. So you can see, as you can see here, and the cubic interpolation is a third order polynomial, and the quadratic interpolation is using the fourth order of a polynomial. So by default we use monotonic cubic. Okay, so I also provide the mass function. So some for some plots we might want to see the differentiate the slope of this curve. So in this plot, the slope means the GN, the transconductance, because it's the current divided by the difference in current divided by the difference in the grid voltage. So when we select that, we can see the GN. So the label changed for the y-axis. So we can see the GN at different plate voltage versus, sorry, the okay, each curve is a plate voltage, and we can see the GN at each grid voltage versus the plate, yes, the GN at different grid voltage. Okay, so you can play with the interpolation later and get a slightly different result on the GN plot. And actually, I have a problem with this feature. I'm not sure it's done correctly. And for this example, the result seems to be reasonable. And let me use the 300B as an example. So so this is the measurement data for a 300B. So let's open the same function again. Use grid voltage as the x-axis, and check on the GN. So this is the plot here is a little weird to my eyes. So but what I found is, if I use higher order of interpolation, the curves becomes more reasonable. Also, if we play with the different algorithm, it will also change the result. So I'm not very familiar with this plot. So I'll leave it to you guys to determine, whether there's something done wrong by me or it's like this. So I'll upload. Actually, the software is already uploaded to the etracer website. So please download it and play with it. And if you have any comment or you think there's anything done wrong, please let me know. Okay, that's it. Thanks for watching my video, and happy curve chasing. I'll see you next time.